Hi everyone, this is our second to last experiment of this semester. It's called acid-base catalyzed ring opening of epoxide. In the post-lab analysis, you will need to firstly predict the ratio difference between the two reactions, and then compare the results from what you got from the experiment. And then if your prediction match the data analysis, then you confirmed what you predicted, right? If the data analysis or the result you got from data analysis do not match what you predicted, you will need to also analyze why that's not the case. Okay, you can think of any experimental errors that may lead to this, or any experimental conditions that was that would result in the differentiation. Alright, so in this experiment, you will be working in a group of two, where one student will run the acidic epoxide ring opening, the other student will run the basic catalyzed ring opening. Okay, then you will be sharing the result you got from both, and then use the GC data from ELC for analysis. Alright, so firstly, let's talk about epoxide ring opening reaction. The three-membered epoxide ring was very unstable. It can be cleavaged in both acidic and basic conditions. Because the inherent ring strain was very large, so it's going to be subject to nucleophile attack pretty easily and pretty readily. And then let's talk about the reaction itself. So we call the ring opening reaction of epoxide in either acidic or basic environment to be regioselective and stereospecific. Firstly, let's talk about the difference of these two names. An example of regioselectivity will be hydroboration reaction, right? So you use a reduction, and we know that the proton will be added to the more substituted side will be favorable, right? So you will be creating the second product as a major product, while the first one being the minor product. And in this reaction, there are two sites that can be reduced, right? And the reaction is selective between the two sites. So we call that regioselective. If in a reaction, you only form, for example, this product using a reducing reagent, then we'll call this regiospecific, because you formed 100% of only one regioisomer. Okay? And then we'll talk about stereoselectivity and stereospecificity. Alright, so we know pretty well that an alkene can be oxidized using MCPBA, right? You're going to be forming a ring, a three-member ring, epoxide. And in theory, you're going to get 50 to 50 ratio of the stereoisomer, right? Is this reaction stereoselective? No, because you're creating 1-to-1 ratio, which means it's not selective. If you use another catalyst, that will give you 80% to 20% of product 1 and product 2, we will call the reaction to be stereoselective. Okay, so basically you're creating an equal amount of stereoisomers during this reaction or during this creation, right? And when coming to stereospecificity, we'll probably use SN2 as a reaction to explain that. So we know that in the SN2 reaction mechanism, the new nucleophile is going to attack from the backside compared to the old nucleophile. The reaction will lead to configuration inversion. We also got backside attack, and only one product, which rendered it to be stereo-specific, right? Which also came from configuration inversion. If in a reaction you only produce one stereoisomer, then we're going to call this reaction to be stereo-specific. All right, after figuring all those out, we're going to come back to our reaction. Well, as we said, the reaction is very stereo-specific because it's going to form go in a SN2-like manner. It's not exactly the same, but they're similar. The new nucleophile is going to attack from the backside compared to the epoxide, which will make the reaction stereo-specific. And secondly, for regional selectivity, it's going to be different from acidic solution or acidic condition or basic condition. We're going to talk about acidic condition first. In an acidic condition, the nucleophile is going to attack the more hindered carbon. This one kind of was similar to a SN1 manner because the mechanism in acidic condition will be the oxygen being protonated by sulfuric acid first, and then the more substituted side will be attacked by methanol, being the nucleophile. After opening the ring, the methanol will be deprotonated, which rendered you the final product, right? And the minor product will be methanol being the nucleophile attacking the less substituted site, which will lead us to the formation of minor product. Although it's not favorable, but there's still going to be some being produced, which is the definition of regional selective. Okay. And if you go to the basic condition of ring opening, then firstly, in the basic environment, your original nucleophile methanol will be deprotonated into methoxide, right? Methoxide is carrying a negative charge, is a very strong nucleophile, and that's going to be the nucleophile to attack, right? You can think of this as kind of an SN2 manner when the strong nucleophile is going to prefer the less hindered site, which means that the site is going to be less substituted. Kick off the carbon to oxygen bond, break that, and in the end, after the workup, the epoxide will be protonated and restored and form the alcohol product. Again, in this way, the minor product will be formed when your methoxide nucleophile is attacking the more substituted site and being protonated. Okay? If I ask you to predict in which condition, acidic or basic condition, will the reaction be more selective, and why was that? What will be your choice, or what will be your answer? Think about it. And you may want to compare them in different conditions and strong or weak nucleophile in that way. Okay? And you're also going to need to rely on this experimental result to find out which one was the experimental result. Alright, so it mentioned here that the purpose was to react the same epoxide in both conditions, use GC data to prove or disapprove the theoretical prediction, also calculate the exact product ratio obtained from both reactions. So we're going to talk about GC. GC is called gas chromatography. And, well, we've done chromatography before, right? For example, thin layer chromatography, TLC, which is the first experiment in 2311 or 2411 lab. All chromatography follow the similar mechanism. So you have a stationary phase, you have a mobile phase, right? If you go to the very last page of the slide, then the tiny guy, running guy, will be the stationary phase, while the peach or the watermelon it carries will be the compound you want to separate out, right? So basically, you want your, the tiny guy will be the mobile phase. You want your mobile phase, the small guy, to carry products of different polarity to run on the same road, and the road will be stationary phase, right? The road can be very rough, it can be very polar. So the interaction between your guy and the road will be different since it's carrying fruits of different weight. The heavier the product is, the more polar your product is, the more interaction it's going to have between the guy and the road, right? It's going to tend to linger behind, which renders that the person who is carrying product of less polarity will run the fastest. And your stationary phase that's carrying the most polar compound will tend to linger till the end. Does that make sense? So if you use a TLC, solvent front, that's where they all start from, starting line. Then we would assume, we would predict the purple line to be more polar because it tends to linger behind and have a smaller RF value. And at the same time, the green dot will be less polar since it doesn't interact with a very polar surface much, and it's going to have a larger RF value, right? That's a way for you to predict which product is which dot. And in the GC chromatography, it's pretty similar. So this is showing you the inside of a GC, and I'm going to show you that in the class as well. What happened is that, so we have a carrier gas. It's mainly an inert gas. It's either nitrogen, sometimes helium. And the inert gas is only the mobile phase to carry your product through the column. It's not going to react or anything. It's just carrying your product. And after you injected a very small amount of your product into the ignition chamber in very high temperature, your product mixture is going to be vaporized instantly and being carried by the carrier gas into the very polar column. And they're going to be separated out in the long column. In the end, they're going to be detected by the detector and show up in the data analysis system. The data analysis system will remember and record how many dots or how many compounds are collected at this retention time, right? And the number of the dots, basically the area of the peak, will suggest how much of this compound it has. So the GC analysis data you're going to be seeing are mostly going to look like this GC spectrum. So at the bottom is retention time, T or minute. Right? The first peak are normally solvent being used to dissolve your product mixture. And this time we're going to use methanol, if I remember correctly. The second peak and the third peak will be your product mixture, right? If you calculate the area of these two peaks, it's going to give you the ratio of the two products, how many you have. So now there are several questions you want to consider. Firstly, retention time. What does it tell you again? Well, we mentioned that the longer it's staying in your column, the longer the retention time will be. That's going to mean your product is more polar or less polar. If it stays in your column longer time, then it's going to be more polar, right? Which means that product B have longer retention time is the more polar compound, which render compound A being less polar, right? So you will need to do two things. Firstly, predict your product mixture. Product mixture. You're producing two products. What are they? Secondly, determine the polarity of the two products. Thirdly, assign the two products onto your spectrum, onto your GC spectrum. Fourthly, after you determine the ratio of the two compounds, you will need to determine the ratio of the two products. Lastly, does the ratio coincide with what you predicted? If it doesn't, what do you think happened? And if it does, then congratulations, you got the correct prediction, right? There are some occasions you will run into spectrum that are like here 1, 2, 3. So there are 3 products from both two spectrum, right? They have the same mixture, just different ratios. Retention time. That's a solvent. If you only judge by the ratio differentiation, you know that you're producing more of B. However, you cannot assign B to the larger peak because we know that retention time is the only sign that will tell you the identity of your product, right? Retention time refers to polarity, refers to the identity of your product. If you know that you have the same mixture of different ratios and by doing GC analysis, then the products that's showing up at the same retention time have to be the same product. Same case. If they show up at the same place, they're the same product. Does that make sense? I see a lot of the mistakes being made for the post-lab analysis of this experiment, especially. So just a hint or just a reminder, right? Follow the retention time rather than the ratio. not the ratio, only the retention time. And also, well, let's see, 1, 2, 3, 4, 1, 2, 3, 4, OH. If they both have an OH, they're both alcohol, they have the same number of carbons and protons. Which compound of these are going to be more polar? We'll designate the B to be more polar, right? Because the hydroxy group, being the very polar group, is not inside of a compound, so it has more space and chances to be interacting with other molecules, which will make it more polar, which also makes product B to be more polar. And should they have longer or retention time or shorter retention time? More polar, more interaction, and longer retention time. Okay, and these are all the same. So think about it before you assign protons and before you do analysis. That's all I can think of for the post-lab analysis. And make sure to assign those, because there are going to be points assigned for correctly assigning your products to the GC peaks. Okay.